Okay, and we're back for our third talk of this session. And now we're going to have Omer Shlomovits. He's founder and CEO of Ingonyama, which is building hardware for zero-knowledge proofs, if I understand correctly. Omer has also been co-founder of past companies and efforts, such as Zengo, and has been involved with the MPC Alliance. And he has a nice title, From NAND to Verifiable TETRIS. Thank you very much, Omer. The floor is yours.
Thank you for inviting me. The title is a tribute to the now famous course, From NAND to TETRIS, which basically teaches the foundations on how to build a computer. So I'm not going to do that for ZK computer, but I am going to share my knowledge and insights from the past year also on working on zero-knowledge hardware. So to start with, I mentioned zero-knowledge and hardware, so I need to scope it a bit so that we're all on the same page. And like every good technology, we have three pillars, right? So we have algorithms, we have software, and we have hardware. In our context, let me give an example. So Go16 is a very good example for an algorithm. A software might be some implementation in C++, and also some idea on how we can maybe, let's say we have two elliptic curves as part of Go16, we can run them in parallel because they are independent, right? So maybe this would help us. However, in hardware, we talk about the physical. So I have an actual clock that runs at some frequency f, and I want to optimize. I want to optimize on the clock cycles. I want to optimize on some given area. I want to optimize on the power consumption, and so on. Okay? That means that in order for hardware to make sense, we need to focus on real-world systems, which means that for the sake of this talk, we're going to be biased towards Snarks and Starks. I mean, these are the type of protocols that we see implementations, like they have algorithms, they have software, and they are also in production. And it also means that the main problem or the main bottleneck computationally is the prover. I'm saying the proving time, the prover time, obviously it can be a bit more than that. So the trade-off space is around the prover. So what's going on in zero-knowledge hardware as we speak nowadays? And as you know, hardware can be very competitive business. So I guess one point to make is there's a lot of action, but most of it is under the surface. So let's try to pick up some signals on what's actually happening. And one good way to look at it is let's see what's happening in academic research. So the last year was been really prolific. Many interesting papers came out, starting from PipeZK. So it stands from Microsoft Research and collaborators. Pipe is for pipeline, which is the common way we basically design hardware, and in a pipeline way, and zero knowledge. So basically they took Go16, which has two components basically that needs to be accelerated and kind of simulated a chip that can run it. Later came Pipe MSM from yours truly and collaborators, where we focused just on one of these cores, which is the multiscalar multiplication, and we actually provided implementation over FPGA. It was even improved afterwards by Jump Crypto guys, something called Cyclone MSM, that was focused just on the FPGA and was motivated by competition I would show you in a moment. Let's not also forget GPUs, so CUZK, like it's Q is for CUDA and ZK is zero knowledge. Again, let's take Go16, put everything on a GPU, and make it really, really efficient. So all of these and much more that I left out happened just the course of, I don't know, last 12 months or so, which gives you some kind of sense. It's not only that, maybe you can also notice that most of this research came from industry or industry and academia. Now, industry was also pushing really hard towards fast implementations of ZK hardware primitives. So as you can see, this is a very significant price amount. I don't know if there is an equivalent for that. So if you were a developer that went to and tried to work on this MSM or NTT, which is another IP core or computational problem to be solved, and you could have get really nice amount. This is, by the way, referring just to the MSM on GPU and FPGA, right? So this is like an industry-led effort that gives us, again, a bit of a sense on where we stand today when you talk about hardware. But I guess it raises the question, right? Why hardware acceleration to begin with? I mean, if you'd ask me why I started my company a year ago, I don't have a good answer, right? So let me try and explain the intuition, maybe in like more of a visual way, which is why I'm going to go into gaming, to what are we looking for in hardware acceleration, and maybe it will answer on why now, why all of a sudden all of this interest around hardware acceleration. So bear with me. I'm going to start with 25 years ago. This is a game called Quake. This is state of the art in terms of algorithms and software, right? It was written, it was one of the best games ever created, was written by like the best game developers in the world. And obviously it's very ugly, right? But we know it now because what we are used to is something like this, right? This is the latest Call of Duty from this year. You can see the image is way like brighter, cleaner, and so on. And we ask ourselves, so what's the difference? What happened in this like 25 years? And the answer is, what happened is GPU, right? So this is another type of hardware, and here NVIDIA done us the job of kind of taking this Quake game from 25 years ago, using the GPU technology called RTX, and recreating the game just based on GPU. So you can see the amazing difference, and what it basically needed, they need to do is you needed to run the same, like it's called rendering. So this is like CPU rendering on like the RTX off, and once you apply the GPU, so then you basically run and render the picture many times a second, okay? So many times in 1 second you need to render the picture, and then you get this like beautiful image, right? So what I'm going to claim is that this is going to be just the same with zero knowledge, okay? And let me try and prove it to you. But to do so, I want to take one step back and explain about multiplayer games. The reason is that for zero knowledge to make sense in the context of gaming, we do need to go into a setting where we have multiple participants or gamers, okay? And I hope it will make sense for you in a moment. This is an example of Fortnite. It's a game played online with 100 participants or players. So there are two common ways to run a multiplayer game. One is a server and a client, and the other is a peer-to-peer. When you have a server and a client, so basically this is the most common way, and the server is kind of like a centralized service provider that's supposed to be authoritative, meaning it's kind of like the police. And the reason is that every player would send information to the server, and then the server needs to share this information with all the other players in the game. And so obviously it's very communication heavy, which is one bottleneck, but it's also computationally heavy because the server needs to make sure that every step that the player took is actually according to the physics of the game or to the game engine, right? And there are a few issues with this common model of client and server. One is ownership, so it's very hard to claim some ownership on some item, some sword or something in the game when you have this third party, right? It's not a participant in the game. It's like someone injected this third party that now basically has ownership. It's also very expensive, so it's mostly more than one server. It's multiple servers, and they need to run this very sophisticated logic, which makes it so that they need to be very strong servers, powerful servers, and you need many of those. It also comes to scalability, right? There is so much you can get in communication between all of these participants when you go through a single point. And the obvious is privacy, right? It's, again, a third party, not part of the game, that now has the same view that you have. The peer-to-peer method seems to solve at least some of these problems. However, there's a bigger problem now that you can basically cheat, right? So one player can send to another player that he can now, or she can now fly and just move very fast across some map. So it's another issue, okay? Okay, so now that we got this background cover, let's see what happens when we apply zero knowledge. So first, let's apply it in the peer-to-peer case. And obviously, with verifiable computation, we can fix cheating in a way, right? So the players would also send a verifiable, publicly verifiable proof of every move that they are taking. And basically, now you can kind of, if someone is cheating, it's not like one against another, you can just flag the proof and say, okay, like, I have a proof that I was not a cheater. So this is nice. What's even nicer is that we can even also remove the trust from the system, right? So now basically everyone can be a server, right? So imagine that the server is now sending proofs that computation was done correctly from the players that actually sent to him these messages. So now the players don't need to trust the server because everything it does, it's verifiable. So this can be nice. Like every one of us can become a server. It can be like private servers. You can maybe also think about how it solves something about ownership and so on. So no more, I don't know, Blizzard and such kind of involved in the game. It can be one of the gamers as well because everything is being like proven. And finally, we can even solve scalability if we look at the client-server setting, but from the other way, right? So now, instead of the server doing the police work of checking that all of the proofs for checking that all of that no cheating happened, now we can just verify, like in batch, once every some time or every few moves, it can verify the steps that any of the players took, and basically remove a lot of the computational overhead that the servers now have, and maybe we can extend and have more servers, more participants, and so on. So what's the problem here? The problem is that we need many zero-knowledge proofs to run in the same second, right? Just like as we needed with GPU to render the image many times per second, now we need to run proofs many times per second. Okay, so I hope you see kind of the analogy on how this can be basically like ZK can disrupt. And by the way, I'm not saying it lightly. Like this is like a validated idea. I mean, if anyone wants to discuss, I'd be happy to kind of share more information. But this is valid. Like gaming, as we know them, can be disrupted. Like the server, until now, let's say we are used to 100 participants in a game. We can now do 1,000, 10,000. I mean, once we'll have this many zero-knowledge proofs per second. So this seems like a very ambitious goal. Like we are not there. But how far are we? Okay. And this might also give you an understanding on why we're talking about hardware now. So I collected some data points. So if I want to prove ownership of a CryptoPunk, it takes me to on the chain, it takes me 25 seconds to do so, right? A zero-knowledge virtual machine of type RISC-V, it now runs like a 70s computer, okay? This is the speed. Machine learning of something that is actually useful, right? Like inference in the cloud, and also the Ethereum virtual machine, right? Both of those are taking a few thousands of a second to actually run. So these are like real-world useful examples. Even if we go to costs, right? So right now, how much time it takes to actually run something like a zero-knowledge bridge interoperability between chains, we are talking about a few thousands of dollars. So the answer is that while we can argue that creating proofs is very computationally intensive, it takes like a lot of time for real-world use cases, the facts are that we are not far, right? Like we are, I don't know, 2-3 orders of magnitude from like having ZK in the wild doing stuff that are like in speeds that make sense to us, right? Many times per second. So the solution to what we need is, instead of a GPU, a ZPU, right? Makes sense. And for the rest of the talk, I want to try and answer 2 questions. One is, what goes into a ZPU? I mean, and obviously standardization can be very helpful, so I'll try to give some slides with, I hope, some intuition about what's a ZPU, because we know what is a GPU, or if you don't know, it's very simple to explain. So let's try to understand what is a ZPU. And then, since it takes time to build ASICs and chips, like a few years' time into the future, what can be done until that point, okay? So how do we identify a ZPU when we see one? So let's start with what it's not. Okay, this is a NOT gate, right? I promised Boolean gates, so here is one. So the most famous cryptography accelerator that we have today, or the most popular, is the AES-NI instruction set, okay? So this is very far from what we want in a ZPU, since this is basically the AES. It's a very standard fixed algorithm, while zero knowledge is, as you all know, a moving, evolving target. So it's going to be problematic just to kind of imagine this model. it can also not be just a CPU, right? Like we have the modern CPU, we've like done decades of research and development on having good CPUs, but it's not going to be good enough because CPUs are mostly for integer and bitwise arithmetic. So they can work, I mean, this is what we see today in practice, but we are losing a lot on this, like not being native in the arithmetic, like not working under like finite field arithmetic. So this is, I guess, a good starting point. So we need a chip that would be able to do modular arithmetic efficiently, right? So this is supposed to be like the basic language, the basic operations. It opens up some questions. What is the field that we want to work? Because it can be very significant, the size. Just think about like if it's a 64, 256 bits, very big differences. And also, can we do something more specific to ZK, right? We already know that we want to solve or to accelerate ZK, what can be done? So obviously, there are primitives that can be added, that we can add. So polynomial arithmetic over finite fields is one thing. This is a good, like the example here, the canonical example is to do FFT, which is a very common operation today in Snarks and in Starks mostly. And can we do, we can also do elliptic curve operations and arithmetic. Here MSM is the model. And also vectorized arithmetic, which is what we see in all of these algebraic hash functions and more. Now, one important note to understand is that the more we make the chip complex in terms of adding to it operations and so on, so we are going from small area, also small cost, also low cost, and again, performance and power, to something which is like, bigger on all of these matrices, okay? Right, so this is going to be a very kind of opinionated list that I gathered from the team, the company, the engineers, kind of trying to understand. Basically, as I mentioned before, one of the parameters of a chip is the size of the area of the chip. So how can we make it smaller, or how can we kind of be in a good position in this scale? So if we can standardize, or we can decide to agree on a set of field sizes, right? It's relevant for the finite field arithmetic and also the elliptic curve. Like basically, elliptic curve, it's like coordinates over some field, right? So if we can reach some agreement on I don't know, Goldilocks field is something that everyone wants to see accelerated, this can be the most significant. The second point is that today, at least in academia, with Hyperplon, with Nova, we see a lot of papers going into the direction of let's remove FFT from the equation, or entity, it's the same like FFT, right? I'm using both without kind of separating. However, on Starks, we are basically just doing a lot of entities, also fully homomorphic encryption. But what it means is that if we can somehow decide that, okay, FFT, post-quantum, all of that, it's a few years into the future, but now let's focus just on the entity-less kind of designs, this can also mean a lot. I guess that as an extension, we can talk about specific protocols, because like if we want to just focus on like Nova, for example, then it has a lot of implications on what needs to be accelerated exactly. Like we know the exact things that needs to be accelerated. Finally, there's the vector operations, right? So this is one of the things that I'm afraid of the most is what is the hash function that we want to use? There are still a lot of work and progress on algebraic, on arithmetic hash functions that are not hardware friendly. And it means that we need to kind of figure out how to solve for all of them if we actually want to build a ZPU. Remember, a ZPU kind of need to take all of the computation in ZK and put it on a chip. And finally, and this is actually, it's hard for me to explain, but the arithmetization does have some meaning in terms of like how we treat it or how you think about it in hardware. So again, happy to discuss and kind of, deep dive into any of these points, but take it as a very biased kind of opinionated list. Okay, so what can be done today? And here it's divided into two things. One, we can do science. This is what we do best. And the second thing is, let's see what we have today, existing specialized hardware that we can build on, right? So we already mentioned the GPU. This is Jensen here holding the newest, it's a beast. It's like 4090. It's a gamer's GPU. Like takes a ton of energy, but provides really good results. And this is a tiny, I know it seems big, but the other, besides Jensen, the other hardware is an FPGA. This is the C1100 by Xilinx, which is, again, super small, very energy efficient, and gives also very good results. So let's understand both of these action items. So a selection of questions, stuff that I don't know, just like at least on my mind. I guess something to think about is kind of, let's take the lens of hardware when we design new ZK protocols, which is something that usually we do, but I don't think we do like, we go all the way, like actually implement it in hardware, comparing one to another and so on. The hash functions, as I mentioned, this is an issue, right? So if we can come up with something that is both or kind of has a good trade-off between ZK-friendly and hardware-friendly, right? Hardware-friendly, SHA-256 and so on, Blake, and ZK-friendly, Poseidon, Anemoy, and so on. So if we can come up with some kind of a compromise, or even if we can do some theoretical work that understands the end game for hash functions, like what's the best hash function that ZK can ever have, that would be very useful. Also, when we want to prepare for this world of ZPUs, where basically all of our desires everything is solved, so then what's next, right? The trade-off space is kind of becoming interesting because maybe we can go to a prover that is O of n squared, right? Size of the problem. I mean, we can change parameters and see how it impacts other elements. What's the next in line that we want to improve? And then we have the memory management things in all of Snarks and Starks. Like this is a real pain because I don't know why, but when we are doing today work on Snark, a new protocol or Stark, we just don't think about the blow up in memory. And this is the main bottleneck that today developers are facing, right? Like it's just, again, I'll be happy to discuss it in more details because we collected a lot of data around this particular issue. But memory management is a thing in Snark and Starks. When you go into the interactive zero-knowledge protocols, then they do a lot of work on the communication and memory. Here it's not, but in Snarks and Starks, this is kind of like we only care about, I don't know, the prover complexity and so on. So the last section of this talk is about like what you can build today, right? So we need to understand the hardware that's available to us and how can we access it and what to build, and then I hope to share some examples of stuff that we've done. So we have the GPUs and the FPGAs that I mentioned, and here's like just quick data points on where they stand. So GPUs today are very cheap to buy. I mean, it's not always the case, but today this is it, right? So yeah, it comes from many different kind of macro reasons, but it's the fact. FPGAs are actually cheap to operate, right? Remember that the electricity for an FPGA is roughly like 10x less than the electricity that you need for a GPU. So we also have an access of many GPUs today in the market. This is basically because of the Ethereum move from proof of work to proof of stake. And what we showed, and be happy to share more details about it, is that you can take these like GPUs that were used for mining and repurpose them to do some ZK stuff. It's far from trivial, but it's possible. And we are talking here about millions of GPUs, right? Like there's a lot. FPGAs also, I mean, there's also kind of utilization that can be done because there are data centers that are running FPGAs. In both cases, there's availability in the cloud, right? So this is from AWS, the table, and you can see prices are reasonable. It happens almost across all, like, with all cloud providers. So today, if you want to access an FPGA, you don't need to buy something, plug it, and like figure it out. You can access it, same DevOps experience that you'd have to access any instance of CPU. Some empirical result is that the massive GPU that we've seen before, the 4090, this is one type. There's another type of GPU which is like for data centers, without gaming options and so on. And the gaming ones are better, right? Like in performance. The downside is that they are very big, like bigger than the data center ones, and they take a lot of energy, more than them. In terms of software, there are open source libraries for GPU, and be very happy to discuss those and what can be improved. We work extensively on GPUs and FPGAs, so if anyone wants to get involved writing kind of these low-level primitives, I'd love to help. And we also started some efforts around FPGA open source and development, right? For like this Cloud ZK is a nice way to use this cloud resources FPGA to get some acceleration happening, and soon I hope to share some results on what can be done with this as well. So what we can build today, and here I divided it into two types. So we have the infra and foundations, and we also have the frameworks integration, okay? So let's start with the infrastructure, right? So if you are a specialized, like if you are a company or something like this, you can come up with some ideas that can leverage this technology, this hardware. You can build a prover as a service that can be very useful to accelerate provers. You can also build a decentralized version of it, which is even better, right? Like this is the point of ZK, kind of facilitate decentralization. There's also what I call the ZK marketplace, which is on the one hand, you have a lot of compute power, like these GPUs that we talked about that used for mining, let's say, and FPGA data centers. And on the other hand, you have zero-knowledge applications. Can be like ZK rollup or something. And then someone comes to the marketplace, want to rent or to use some of these like computational resources and apply them to some of these problems, right? So this is another kind of a game that can happen. And obviously there are some applications that are already in production in the wild or getting there that definitely can leverage hardware acceleration, right? So Filecoin it's not exactly a miner, it's a different process. Filecoin is a decentralized storage solution. So definitely they are using today GPUs. There's dunk sharding, which is not using ZK per se, but it's using polynomial commitments, which is kind of the basic same primitives are used to accelerate both. And also framework integration. Eventually, we want to allow devs to not think like, I guess that in the near-term future, we want all of this integration with Arcor, Circom. These are like a couple of examples. There are others that are developers that are coming today to use zero knowledge. This is basically what they are facing. They need this to use some toolchain to build application, right? It can be, I don't know, zero-knowledge machine learning, right? So you need to pick up something. So if you allow them to have first-class citizens, these FPGAs and GPUs, they can benefit from it quite a lot. And I hope that in the short-term future, we'll have this option, baked into these frameworks. Okay, let me finish with a couple of examples of how to apply what I just said in reality. So Elio is a blockchain with privacy. They get privacy with using zero knowledge, but they also incorporated zero knowledge or Snarks, and it's the same one as part of their consensus mechanism in some nice way, okay, which I will not go into details with. So we experimented with implementations that are based on GPUs, on FPGAs, and also both GPUs and FPGA together. This is just like one of our like setups that we have in the lab used for experimentation. And it's hard to see, but you have like this massive GPU there, but you also have an FPGA. Usually in the application of mining, electricity is important, right? If you look at, let's say, Bitcoin, at some point it became just about getting the price of electricity lower and lower, okay? So it means that FPGA has some advantage when you think about it long term. Now, the way that we try to analyze a protocol, this is Marlin, right? Marlin is a protocol. And this is how we analyze it step by step in terms of like the exact cost that you take in terms of running it. Now, as you can see here, and this is just our way of analyzing it, you have some computational bottlenecks. Like these are the colored boxes. One is the MSM, one is the FFT, and I guess you can also double click on some of them and kind of open some more bottlenecks and see some more computational bottlenecks. And just to give you some details on this protocol based on this estimation, so there is some elliptical, right, like this BLS. Mostly it's MSM, this primitive that I mentioned, and FFTs. Okay, so it means that if we can accelerate both, we are in a good place, right? Like we can achieve up to something like this factor, right? Imagine that both of these MSM and FFTs are 0. So I guess that the proofs per second that we got, like this factor 8 or something, should be kind of make sense. Another example is the rapid Snark, or how we call our version of it rapid Snark. So what's rapid Snark? This is one of these frameworks, right? So before I gave you an example of this app-specific, and now it's an example for one of the integration with frameworks. So this is a popular one. I mean, if you go and learn about ZK from 0xSpark or something, usually you end up using this toolchain, okay? It's written in C++, and there's a lot of, there's a frontend called Circom, and also some JavaScript around it, and so on. So we basically what's running under the hood is Growth 16, optimized assembly and such, uses some elliptic curve, another one, BN254, which is Ethereum friendly. And under the hood, we have, again, entities and MSMs. So this is the division. So note that here it's not just one, we have two types of MSMs, like we have two elliptic curves, so it's a bit more complex, right? So in our setup, we actually used two FPGAs, right? One for each MSM. And today what's happening is that your projects that are being run using Rapid Snark, they are using a beefy CPU. It costs quite a lot per hour. And it actually performs not so bad, right? But it has a very, like the developer experience is very, very smooth, right? Like you go to AWS, you rent this cloud instance, and you can run basically ZK. I mean, it's more complex. By the way, advice, if you want to understand zero knowledge, try to run a zero knowledge yourself, all the way through whatever ceremony and like key generation and so on. Try to get the feeling of it. I'm sure it would open your eyes. So our goal was to get to the same cost. We didn't want to get, you know, it's not fair if we are going to pay 10 times for 10 times the speed. But we wanted to get some acceleration, right? So basically we aimed for, this is the example from ZK Attestator by Isan, and he kind of got to 25 seconds, what I told you, to kind of prove the ownership of some asset on the blockchain. So there are some challenges, as I mentioned. One is about the fact that it's two elliptic curves, not one. And another one is that the hardware basically, when you compare a CPU, which basically all the time, it's like 100% occupied, all the time is working, to a system that now has two FPGA cards. So the system is either like you have times where the CPU or the FPGAs are idle. So the resources are not fully utilized. It can be improved a bit if you try to measure, instead of latency, throughput, right? Like how many proofs per second you can actually get, which is also what we wanted to do in the mining example. The final, I will not go into the final challenge here, but just at a high level, entity, like you want to support different sizes of problems, right? This is a framework. So you want to support circuits of size, I don't know, 2 to the 20, but also 2 to the 25. And entity becomes an issue once you go into a bigger and bigger circuit. So that's another thing. We got some improvement. We're still working on it, and also other integrations, and we'll be happy to share some open source stuff very, very soon. And with that, I'll end and open for questions.
Questions?
I actually have a question. You mentioned the idea of prover as a service. And I think that there is something very interesting that comes out there because, of course, once you delegate the prover algorithm, you're giving up a certain amount of privacy to the computer that you're delegating, right, to the cloud. And so I know that there's like some people also looking at kind of how to make that in a more kind of privacy preserving way. I'm wondering if you have like a sort of either like a insight sort of on what's the state there.
Yeah, that's a very good point. So I talked about it with Professor Canetti yesterday, exactly the same point, because as you understand, all of what I talked about is the verifiable computation. We didn't talk about the privacy part, and privacy is like a great benefit of using zero knowledge. And as I mentioned, Alio, for example, is blockchain. From example one, they are focusing on privacy, and they want the user experience to be very smooth. So they want acceleration, but also privacy. So how do you do both? Because once you go into privacy, into hardware, it creates all this new challenges like constant time and so on. I don't even know what it means. So they came up with, I don't know, I know that they have some work that is, but I think it's like very, I don't think they published anything, but they do have some way to actually outsource. Like they can separate the privacy preserving parts from the heavy computation parts. So therefore you can kind of take it and move it into like the computational heavy parts to the cloud. So they came up, I think, with a solution, but it's definitely an open research question, and I think it can be very interesting to kind of benefit from both the privacy and acceleration by doing this separation.
You mentioned the importance of hash functions that are friendly with respect to zero-knowledge proofs and hardware. Would you say, let's say in the use case of gaming, the lack of standards for that, is that an hindrance, or is more research needed until getting to a point that where it would make sense to standardize something?
Yes, so I'll share my personal experience. Like MSM and NTT, you see it, like it repeats, and ZK has been with us for a few decades now, and it will probably not change. Like maybe the ratio, maybe more MSM, less NTT, or the opposite. Hash function is something. Let's say hash function takes like 5% of the computation, 10%. Let's make it round. So it means that the max that you can accelerate if you put the hash function outside of the hardware is 10x. This is not enough. This is not enough to get to the gaming scenario that I was pointing out. So you want the hash function to be part of the computation. You want the glue logic and all of this, like everything that's not the main computational problems, also to be in the hardware. Now, the thing is that now the industry kind of adopted Poseidon. But we already know they are better than Poseidon, right? Like it was presented yesterday. So if we are implementing hardware for Poseidon, but then the industry is moving to something else, the hardware is not worth anything. So we need to come up with some kind of a way to de-risk it by kind of having a design that solves for all of, like a family of hash functions. And to get to this point, you obviously lose something on performance, right? Like that's the spectrum. So the more we can kind of get, some stuff that are fixed knowledge that we know on hash functions, how they're going to behave, that would be better for hardware.
Okay, thank you. So it looks like in this case, the driver for standard is more the hardware part than the ZK part.
Yeah.
For the case of the hash functions.
Yeah. Mm-hmm.
Any other question?
No one wants the microphone? No?
Okay, let's thank the speaker one more time.